There's a peculiar feeling that sometimes washes over physicists late at night, when the equations have finally balanced and the predictions have come true once again. It's not quite triumph, it's something closer to vertigo, because the mathematics works too well. Consider this. A mathematician sits in a quiet room, playing with symbols on paper, no telescope, no laboratory, just abstract reasoning about curved spaces and imaginary numbers. Years later, astronomers point their instruments at the sky and find that the universe behaves exactly as those symbols predicted. Light bends around massive objects. Time dilates near black holes. The cosmos conforms to equations written by someone who never left their desk. How is this possible? We've grown so accustomed to the marriage of mathematics and physics that we forget how strange it is. We teach children that math describes nature as if this were obvious, inevitable, unremarkable. But it isn't obvious at all. It's deeply, profoundly weird. Mathematics began as something we invented, a tool for counting sheep, dividing harvests, measuring land. Human constructs, born from human needs. Yet, somewhere along the way, these invented symbols started revealing truths about the universe that no one had asked them to reveal. They began predicting things that hadn't been observed yet. They started telling us what must be true, even when our senses said otherwise. Isaac Newton invented calculus to describe how objects fall and planets orbit. The mathematics was elegant, powerful, shockingly precise. But it was just the beginning. As science advanced, the pattern repeated itself, again and again. James Clerk Maxwell unified electricity and magnetism using equations so beautiful that physicists still pause to admire them. Those same equations predicted the existence of electromagnetic waves traveling at a very specific speed. That speed turned out to be the speed of light. Maxwell's math had accidentally explained what light was. Einstein took this even further. He didn't start with observations of gravity. He started with a thought experiment and some geometric reasoning about curved space-time. The mathematics that emerged told him that gravity wasn't a force at all, but the shape of space itself, bent and warped by mass and energy. It sounded absurd. It violated intuition. But when astronomers looked at starlight bending around the sun during an eclipse, the deflection matched Einstein's equations to a precision that made headlines around the world. The universe, it seemed, was doing exactly what the math said it should do. This is what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics. Unreasonable because there's no obvious reason why abstract symbols manipulated according to arbitrary rules should tell us anything true about physical reality. No reason why the language of mathematics should be the language nature speaks. Yet it is. Think about quantum mechanics. The theory is famously strange, filled with particles that exist in multiple states at once, with waves that collapse upon observation, with entanglements that Einstein himself called spooky. But beneath all that strangeness lies mathematics of extraordinary precision. Quantum equations predict the behavior of electrons, the spectrum of light from atoms, the structure of molecules, the physics of semiconductors. They work so well that the entire digital age rests on their accuracy. Your phone, your computer, the GPS satellite telling you where you are, all of them function because quantum mathematics describes reality with exquisite, unforgiving precision. And here's what haunts us. These mathematical structures existed before we discovered them. The Schrödinger equation was true before Schrödinger wrote it down. The geometry of curved space-time was real before Einstein recognized it. The properties of prime numbers were fixed before any human mind conceived of number theory. We didn't create these truths, we stumbled upon them. This raises an uncomfortable question. If mathematics exists independently of us, where does it exist? Not in physical space. You can't find the number pi by digging in the ground or looking through a telescope. Not in time. Mathematical truths don't change as the universe ages. They seem to inhabit some other realm entirely. A Platonic space of pure form, eternal and unchanging. Yet somehow, impossibly, that abstract realm connects to this physical one. The eternal truths of mathematics reach down into the temporal world and dictate how particles move, how stars burn, how galaxies evolve. The precision is what unsettles us most. It's not that math approximately describes nature or gives us rough guidelines. It's that the correspondence is exact. When physicists calculate the magnetic moment of an electron using quantum field theory, and then measure it in experiments, the agreement extends to 12 decimal places. 12. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. This isn't luck. This isn't coincidence. Something deeper is happening. Sometimes the mathematics knows things before we do. Paul Dirac was working out the quantum mechanics of the electron when his equations insisted that there must be another particle, identical to the electron, but with opposite charge. Dirac trusted the mathematics. A few years later, physicists discovered the positron, the electron's antimatter twin, exactly as the equations had predicted. The math had seen it first. Or consider the case of quarks. Murray Gell-Mann was organizing the zoo of subatomic particles discovered in particle accelerators when he noticed a mathematical pattern, a symmetry group called SU3. The pattern was beautiful, but it had gaps. The symmetry required particles that hadn't been observed yet. Gell-Mann proposed that all these particles were made of smaller constituents, quarks, arranged in patterns dictated by the mathematics. At first, many physicists were skeptical. Quarks seemed like mathematical abstractions, not real objects. But experiments eventually revealed their existence, along with the intricate quantum rules governing their behavior. The mathematical pattern had been real all along. We keep discovering that nature uses mathematics we've barely invented yet. Group theory was developed as pure abstraction by mathematicians in the 19th century with no physical application in mind. 100 years later, it became the essential language of particle physics, describing the fundamental symmetries of the universe. Complex numbers were controversial when first proposed. Numbers involving the square root of -1 seemed like logical impossibilities. Now they're indispensable in quantum mechanics. The universe, it turns out, runs on complex numbers. How did mathematicians know to invent these things before physics needed them? Or perhaps that's the wrong question. Perhaps they didn't invent them at all. There's a pattern here that we can't ignore. Every time we peel back another layer of reality, we find more mathematics underneath. Not different mathematics, not new mathematics. The same eternal structures that pure mathematicians discover through abstract reasoning alone. The universe appears to be not merely described by mathematics, but built from it, woven through with it, perhaps even identical to it. Roger Penrose once calculated that the precision required for our universe to exist in its current form, with galaxies and stars and planets and life, is staggering. The initial conditions at the Big Bang had to be fine-tuned to 1 part in 10 to the power of 10 to the power of 123. That's a number so large it defies comprehension, a precision so perfect it almost seems intentional, as if someone or something was doing the calculating. We stand in front of the chalkboard late at night, surrounded by equations that predict phenomena we haven't observed yet, that explain mysteries we haven't encountered, that reveal structures we haven't imagined, and we feel that vertigo again, that unease. The universe is too precise, too mathematical, too perfect. Wigner ended his famous essay with a question that still echoes through physics departments and philosophy seminars. The miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. A gift. From whom? From where? We've been assuming all this time that we created mathematics, that we're the authors of these equations, the inventors of these proofs. But what if we've had it backwards? What if mathematics isn't our discovery at all, but something we're slowly waking up to, like a dreamer becoming aware of the dream? What if we don't discover mathematics? What if it discovers us? There's a moment in Einstein's biography that deserves our attention. It's 1915, and he's struggling with the final form of his general theory of relativity. The mathematics is punishing: tensor calculus, differential geometry, equations that bend and twist through multiple dimensions. His colleague David Hilbert is working on the same problem, and there's a quiet race between them to reach the answer first. But here's what matters. Both men are working purely with geometry, with shapes and curves and abstract spaces. Neither is conducting experiments. Neither is gathering data from telescopes or laboratories. They're manipulating symbols that describe how space itself might curve in the presence of mass and energy. They're drawing the architecture of reality using nothing but mathematical reasoning. Einstein finishes first, just barely. He writes down his field equations, 10 interlocking differential equations of extraordinary complexity and beauty, and then he waits. Because the equations make predictions that seem impossible, they say that massive objects should warp space-time around them, that light should bend when passing near the sun, that time should slow down in strong gravitational fields, that the universe itself should be expanding or contracting, unable to remain static. All of this from geometry, from pure mathematical form. 3 years later, Arthur Eddington leads an expedition to observe a solar eclipse. He photographs stars near the sun's edge, measuring how much their light has bent. The deflection matches Einstein's equations exactly. The geometry was right. Space really does curve. Reality really does have that shape. Einstein had mapped the structure of the cosmos from his desk. This is where we begin to glimpse something profound. Mathematics wasn't just describing reality. It was revealing reality's underlying form. The physical universe was behaving according to geometric principles that existed independently, eternally, in some abstract space of mathematical truth. Einstein hadn't invented these principles. He'd uncovered them. He'd found the shape beneath reality. We're taught to think of the universe as fundamentally physical. Atoms and energy, particles and forces, matter and motion. Mathematics in this view is just our tool for describing all that physicality, a language we invented to talk about things that would exist whether we talked about them or not. But what if we have the hierarchy inverted? The physicist Max Tegmark has proposed something radical: the mathematical universe hypothesis. His argument is unsettling in its simplicity. If a mathematical structure is complex enough, detailed enough, complete enough, then it doesn't need anything else to make it real. It doesn't need to be instantiated in some other substance. It doesn't need to be made of anything. It just is. Think about the game of chess. The rules of chess form a complete mathematical structure. They define every possible move, every legal position, every potential game. Those rules exist whether anyone plays chess or not. They're eternal, unchanging, independent of physical reality. Now, imagine a structure infinitely more complex, a complete mathematical description of quantum fields, space-time geometry, fundamental constants, initial conditions. A structure so detailed that it specifies every particle, every interaction, every moment of history. Tegmark asks, what would such a structure need in order to be real? What would it be missing? His answer, nothing. It would be complete in itself, self-contained, self-sufficient. We might be living inside it right now. This idea feels wrong at first. We feel solid. The chair beneath you, the ground under your feet, the air in your lungs, these things seem undeniably physical. They have mass and texture and resistance. How could they be mathematics? But consider what physics actually tells us about matter. When you touch a table, you're not really touching anything. The atoms in your hand and the atoms in the table never make contact. What you feel is the electromagnetic repulsion between electron clouds, fields of force described by quantum equations. Go deeper, and you find that electrons aren't tiny billiard balls. They're quantum wave functions, mathematical objects that exist in superposition until measured. Deeper still, and even the idea of particles dissolves into quantum fields. continuous mathematical structures filling all of space, with particles as mere excitations, ripples in the mathematical substrate. Peel back every layer, and there's always more mathematics underneath. Never a point where you hit something that isn't mathematical. Never a moment where the equations point to something beyond themselves and say, "That's what we're describing, that non-mathematical thing over there. There's only mathematics all the way down." The string theorists know this intimately. They're trying to unify quantum mechanics and gravity, and they've found that the solution might require extra dimensions. Not 3 spatial dimensions, but 10 or 11 or even 26, depending on which version of the theory you follow. These extra dimensions are tiny, curled up on themselves in the complex geometric shapes called Calabi-Yau manifolds. Now, we can't see these extra dimensions. We can't visit them or measure them directly. They exist purely as mathematical necessities, required by the consistency of the equations. Yet, according to string theory, the exact shape of these hidden dimensions determines everything we observe in our 3-dimensional world. The masses of particles, the strengths of forces, the laws of physics themselves, all consequences of higher dimensional geometry. Reality would be an echo of mathematics we can't even perceive. This is what we mean by the shape beneath reality. There's a structure, a mathematical lattice, woven through the fabric of existence. We see only its shadow, its projection into the limited dimensions we inhabit. But the full structure exists in abstract space, determining everything, dictating the rules by which particles dance and galaxies spin. Some physicists go further. They suggest that our universe might be just one mathematical structure among infinitely many. Every consistent set of mathematical axioms generates its own reality, its own physics, its own history. These aren't parallel universes in the science fiction sense. They're equally real instantiations of different mathematical systems. Some have different laws of physics. Some have different dimensions. Some have no notion of space or time as we understand them, and all of them exist simply by virtue of being mathematically coherent. This is called modal realism in philosophy, and it's exactly as dizzying as it sounds. Every logically possible world is real. Every mathematical structure that can exist does exist. Reality becomes the complete set of all mathematical truths, and we're merely one chapter in an infinite library of existence. But let's return to our universe, this particular mathematical structure we inhabit. Even here, the evidence keeps mounting. The standard model of particle physics, our most successful theory of matter and forces, is essentially a specification of a particular mathematical symmetry group. Give a physicist that symmetry group, and they can derive the existence of quarks and leptons, the properties of the electromagnetic and nuclear forces, the masses of the W and Z bosons. The symmetry comes first, the particles follow. Or look at the holographic principle, emerging from attempts to understand black holes and quantum gravity. It suggests that all the information in a 3-dimensional region of space can be encoded on its 2-dimensional boundary. The universe would be like a hologram. What we perceive as 3-dimensional reality is actually a projection from information stored on a distant cosmic surface. Physics would be fundamentally about information, about mathematics, about structure without substance. The philosopher Gottfried Leibniz glimpsed this centuries ago. He argued that physical reality was made of monads, simple, indivisible units that had no physical extension, no material substance. They were pure mathematical relationships, and the physical world emerged from their interactions. His contemporaries dismissed this as mystical thinking. Now, we have quantum field theory saying something remarkably similar. There's a particular experiment that haunts physicists who think about these questions. It's called the double-slit experiment, and it's been refined and repeated in countless variations over the past century. Send a single photon toward 2 narrow slits. It passes through both slits simultaneously, interfering with itself, creating a wave pattern. But the moment you try to measure which slit it went through, the wave pattern vanishes. The photon chooses one slit or the other. What's happening? The standard interpretation says that, before measurement, the photon exists as a wave function, a mathematical object describing probabilities. Only when measured does it collapse into a definite state. But here's the unsettling part. The wave function isn't describing our ignorance of where the photon really is. The photon really doesn't have a definite position until measured. It exists only as pure mathematical potential. The mathematics is the reality. There's nothing beneath it. John Wheeler, the physicist who coined the term black hole, spent his later years contemplating what he called it from bit. The idea was that reality emerges from information, from yes or no questions, from binary choices that could be encoded in the universe's structure. He imagined the cosmos as a vast quantum computer, processing information according to mathematical rules, with physical reality as the output. We would be patterns in the calculation. This brings us back to Einstein, sitting with his equations in 1915. He discovered that mass tells space-time how to curve, and curved space-time tells mass how to move. It's a feedback loop, a self-referential system. The mathematics doesn't describe something external to itself. It describes its own behavior, a self-existing equation. What if that's what the universe is? Not a thing that exists and happens to follow mathematical laws, but a mathematical structure that generates the appearance of physical existence. The equation wouldn't need to be calculated by anything or anyone. It would simply be the way the number pi simply is, whether anyone ever computes it or not. We think of physics as the study of matter and energy, of tangible things that bump and push and pull. But every time we dig deeper into physics, we find less matter and more mathematics, less substance and more structure, less thing and more relationship. Perhaps physics is what mathematics looks like from the inside. Perhaps we're made of proofs and axioms, propositions and symmetries, living within a theorem that proves itself by existing. And if the universe is mathematics, pure, eternal, self-sufficient, then we face a new question altogether. If physics is merely the shadow and mathematics the light casting it, what does that make us who perceive both? There are numbers woven into the fabric of reality that nobody chose, numbers that simply are, with no explanation, no derivation, no deeper principle from which they emerge. Physicists call them the fundamental constants, and they define everything about our universe. The speed of light, exactly 299,792,158 meters per second. The gravitational constant, 6.674 times 10 to the negative 11th. The mass of an electron, 9.109 times 10 to the negative 31 kilograms. These aren't round numbers. They're not elegant ratios. They're strange, specific values that appear arbitrary when you first encounter them, and yet change any one of them by even a tiny fraction, and the universe as we know it becomes impossible. Stars wouldn't form. Atoms wouldn't hold together. Chemistry wouldn't work. Life wouldn't exist. We're balanced on a knife's edge of numerical precision, and nobody knows why. Consider gravity. It's the weakest of the fundamental forces by an enormous margin, about 10 to the 36th times weaker than electromagnetism. That seems like a design flaw. Why would nature make one force so much weaker than the others? But if gravity were even slightly stronger, say 1 part in a billion stronger, stars would burn too hot and too fast. They'd exhaust their fuel in millions of years instead of billions. No time for planets to form. No time for life to evolve. No time for anything interesting to happen before the stars blinked out. If gravity were weaker, stars would never ignite in the first place. Gas clouds would drift through space eternally, cold and dark and lifeless. The window for a life-permitting universe is astonishingly narrow. Or look at the strong nuclear force, the glue that holds atomic nuclei together. It has to be strong enough to bind protons despite their electromagnetic repulsion, but not so strong that it binds them too tightly. The actual value sits in a sweet spot barely 2% wide. A little stronger, and all the hydrogen in the early universe would have fused into heavier elements. No hydrogen means no water, no organic chemistry, no life as we understand it. A little weaker, and atomic nuclei larger than hydrogen would fall apart. The periodic table would have one element. Chemistry would be impossible, 2%. That's how much room for error the universe gave itself. The fine structure constant is even more mysterious. It's a dimensionless number, pure ratio independent of any unit system, that determines the strength of electromagnetic interactions. Its value is approximately 1 divided by 137. Not exactly 137, but close enough that physicists have spent decades wondering if there's a reason for this near-integer relationship. There isn't. Not that anyone has found. Yet if that number were 5% different, carbon wouldn't form in stellar cores. The nuclear reactions that produce carbon from helium require an extraordinary coincidence, an energy resonance that happens to match almost exactly the energy of 3 helium nuclei colliding. Fred Hoyle predicted this resonance must exist, purely because we exist and we're made of carbon. He was right. The resonance is there, sitting at just the right energy level, as if someone had tuned it specifically to allow carbon-based life. Hoyle, an avowed atheist, later said this coincidence shook his worldview more than anything else in physics. The cosmological constant is perhaps the most troubling of all. It represents the energy density of empty space itself, what physicists call vacuum energy or dark energy. Quantum field theory predicts this number should be enormous, about 10 to the 120th times larger than what we observe. That's not a typo. Theory predicts a number with 120 zeros, and reality gives us something almost zero, but not quite. It's the worst prediction in the history of physics, off by a factor so absurd it defies comprehension. Yet, if the cosmological constant were anything close to what theory predicts, space would expand so violently that atoms would be ripped apart. If it were even slightly larger than the observed value, say twice as large, galaxies would never form. Matter would be too diluted, too spread out for gravity to pull it together into stars and planets. We exist in the tiny sliver between theoretical catastrophe and observational precision, and we have no idea why. These aren't isolated curiosities. There are dozens of such constants, each precisely calibrated, each sitting in a narrow range that permits complexity and life. The masses of the quarks, the relative strengths of the fundamental forces, the ratio of matter to antimatter in the early universe, the amplitude of primordial density fluctuations that seeded galaxy formation. Every single one appears fine-tuned. This is what keeps cosmologists awake at night, because we have only 2 types of explanations, and neither is satisfying. The first is called the anthropic principle. It says, of course the constants have values that permit life, because if they didn't, we wouldn't be here to wonder about them. We're observers who exist only in universes capable of producing observers. It's a selection effect, not a mystery. This is logically true, but emotionally unsatisfying. It feels like avoiding the question rather than answering it. Yes, we can only observe a universe compatible with our existence. But why does such a universe exist at all? Why are the laws of physics capable of producing observers in the first place? The anthropic principle observes the coincidence but doesn't explain it. The second explanation is the multiverse. It says, there are infinitely many universes, each with different values for the fundamental constants. Most of them are dead, sterile, lifeless. But in an infinite ensemble, some universes will randomly get values that permit complexity and life. We happen to live in one of those rare winners, not because of design or purpose, but because those are the only universes anyone could observe. It's cosmic statistics. Roll the dice infinite times, and eventually you'll get any result you want. The multiverse hypothesis is popular among physicists because certain theories, eternal inflation, string theory, quantum mechanics under many worlds interpretation, seem to predict or require multiple universes. These aren't add-ons to save the theory. They're consequences of taking the mathematics seriously. But here's the problem. If the multiverse exists, it's fundamentally unobservable, By definition, we can't see other universes. We can't measure them, test them, gather evidence about them. The multiverse might be real, but it might also be an elaborate fiction we've constructed to avoid confronting the fine-tuning problem. We've replaced one mystery with another, and there's something deeper that troubles physicists, something almost philosophical. If we attribute the fine-tuning to a multiverse, we've given up on a certain kind of explanation. We're saying that the constants aren't what they are for any reason. They're just random draws from an infinite cosmic lottery. There's no deeper principle, no underlying logic, no mathematical inevitability. It's chance all the way down. But is it? The more we study the constants, the more relationships we find between them. They're not independent variables. They're connected through the structure of the theories that contain them. In the standard model of particle physics, the masses of the particles are related to the strengths of their interactions with the Higgs field. Change one constant, and you'd have to change others to maintain consistency. The code has internal logic. It's not just a random collection of numbers. Some physicists believe we haven't found the right framework yet, that there's a deeper theory where these constants aren't arbitrary inputs, but necessary outputs. String theory, for instance, suggests that the constants might be determined by the shape of extra dimensions, that geometry dictates the values we observe. If true, the fine-tuning wouldn't be tuning at all. It would be inevitability, mathematical necessity dressed up as coincidence. But string theory has its own landscape problem. It appears to allow something like 10 to the 500th different possible configurations, each corresponding to a different set of physical laws. The theory doesn't pick one solution, it allows them all. We're back to the multiverse by another route. There's a third possibility, rarely spoken, but always present in the back of physicists' minds. What if the constants are what they are because the universe isn't just mathematical, but also computational? What if someone, or something, set the parameters? This is dangerous territory. It sounds like intelligent design, like theology masquerading as physics. And maybe it is. But it's also a hypothesis that fits the evidence. The universe behaves like code running on a cosmic substrate. The constants look like input parameters. The laws of physics look like algorithms. And the whole system appears optimized for a specific outcome. A universe capable of producing observers who can understand it. A universe that comprehends itself. The physicist John Wheeler once asked why the laws of physics are comprehensible to human minds. Why can we understand quantum mechanics and general relativity at all? Why isn't the universe so strange, so alien in its fundamental workings, that intelligence like ours simply can't grasp it? Instead, we discover that the universe runs on mathematics we can learn, on principles we can formulate, on equations we can solve. It's as if reality were constructed to be knowable, constructed for the comprehenders. This is where precision gives way to vertigo. We set out to measure the constants, to catalog the numbers that define our universe. And what we found was a system so finely balanced, so exquisitely calibrated, that its very existence seems improbable. We're either fantastically lucky, or part of an infinite ensemble, or something else. Something we don't have words for yet. The constants aren't just numbers, they're questions. Why these values? Why this combination? Why a universe with 26 fundamental constants when, mathematically, we can imagine universes with more or fewer? Why laws of physics that permit complexity, that allow for stars and planets and chemistry and life and consciousness? Why a cosmos that makes sense? We thought we were studying the architecture of reality, measuring the beams and girders that hold existence together. But the deeper we look, the more it seems we're studying something else. Not just structure, but intention. Not just mechanism, but meaning. The code isn't just running, it's running towards something. And if the universe is tailored for comprehension, then perhaps the real question isn't who wrote the code, but who it was written for. We descend now into the smallest rooms of reality, down past the scale of cells, past molecules, past atoms themselves, down to where the universe whispers its most unsettling secrets. Here, In the quantum realm, the mathematics that once seemed so absolute begins to dissolve like ink in water. For centuries, we believed that if we could know everything about a system at one moment, we could predict its future perfectly. Newton's universe was a clockwork mechanism. Wind it up, set it going, and every gear, every pendulum, every planet would follow its ordained path. The mathematics was deterministic, clean, certain. Then came the quantum revolution, and with it, a question that still haunts us. Does observation create reality, or merely reveal it? Consider the electron. You might think of it as a tiny sphere orbiting an atom, like a planet around a sun. But that picture is wrong, profoundly wrong. Before we look, before we measure, the electron exists in what we call a superposition. It is not here or there. It is, in some deeply unsettling sense, everywhere it could possibly be at once. Only when we observe does it suddenly snap into a single location. The mathematics describes this beautifully. Schrödinger's equation traces the evolution of probability waves through time with perfect precision. But the wave function itself is not a thing. It is potential. It is the ghost of all possible futures, existing simultaneously in the darkness before measurement. And then we turn on the light. The wave collapses. Potential becomes actual. The many become one. But why? What singles out one outcome from the infinite field of possibilities? What breaks the symmetry of the wave? Is it consciousness itself? Some physicists have suggested exactly that. In the Copenhagen interpretation, the act of observation is fundamental. The universe exists in a haze of probability until a conscious observer collapses the wave function through the act of measurement. Reality, in this view, is participatory. We are not passive witnesses, but active creators, midwives bringing definite outcomes into being from the quantum foam. It's a seductive idea. It places mind at the center of physical reality, suggests that consciousness is woven into the very fabric of existence. But it raises more questions than it answers. Does it require a human observer? Would a mouse collapse the wave function? A bacteria? A sophisticated measuring device with no consciousness at all? Where exactly do we draw the line between the quantum realm of superposition and the classical world of definite outcomes? And if observation truly creates reality, what happened before there were observers? Did the universe exist in eternal superposition until the first conscious being opened its eyes? The alternative interpretations are no less strange. Hugh Everett proposed that the wave function never collapses at all. Instead, every quantum measurement splits reality into parallel branches. In one universe, the electron goes left. In another, it goes right. Both outcomes happen. Both are equally real. We simply find ourselves in one branch, unable to see the others. The many worlds interpretation eliminates the observer problem by multiplying reality itself. No need for consciousness to collapse anything. The universe is constantly branching, creating infinite copies of itself, of you, of everyone you know, pursuing every possible path simultaneously. The mathematics works. The philosophy is dizzying. Or perhaps there are hidden variables. Perhaps beneath the quantum uncertainty lies another layer, a deeper set of deterministic rules we haven't yet discovered. Einstein believed this. He famously declared that God does not play dice with the universe. Somewhere, he thought, beneath the apparent randomness, there must be a complete set of instructions, hidden from our view, but determining every outcome with absolute precision. But then came Bell's theorem. John Bell proved mathematically that if hidden variables exist, they must be non-local. They must somehow communicate faster than light, violating one of the most fundamental principles of relativity. And experiments performed again and again, with ever greater precision, have confirmed Bell's predictions. The universe really does seem to exhibit the strange correlations that quantum mechanics predicts. Entangled particles, separated by any distance, remain connected in ways that defy our intuitions about space and time. Measure one, and you instantly know something about the other, no matter how far apart they are. Einstein called it spooky action at a distance. He meant it as a criticism, but the universe didn't listen. So we're left with genuine uncertainty woven into the mathematical structure of reality itself. The Heisenberg uncertainty principle tells us there are limits to what we can know, not because our instruments are imperfect, but because nature itself refuses to specify certain properties simultaneously: position and momentum, energy and time. There are conjugate pairs of properties that cannot both be precisely defined. The universe, it seems, keeps some secrets even from mathematics. Or does it? Perhaps we've been asking the wrong question. Perhaps randomness isn't the opposite of mathematical structure. Perhaps it is a kind of mathematics we're only beginning to understand. After all, probability itself is mathematical. The wave function evolves according to precise equations. The outcomes may be uncertain, but the distribution of outcomes follows exact statistical patterns. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions match experiments to 15 decimal places. So, maybe the universe isn't choosing randomly at all. Maybe it's calculating probabilities. But that raises another question. If the universe is a calculation, if it's running a vast computational process that generates reality moment by moment, where does the randomness come from? Does a true random number generator exist anywhere in nature? Or is what we call quantum randomness actually the output of some incomprehensibly complex deterministic algorithm, churning through its steps at a level deeper than we can access? Some physicists and mathematicians have begun to take seriously the idea that the universe is literally a computational process. That reality is information being processed, that what we call particles and forces and fields are patterns in an underlying computational substrate. In this view, quantum indeterminacy might be a feature, not a bug. It might be the signature of a system that's calculating its own future in real time, unable to specify outcomes with infinite precision because the calculation itself is ongoing. The universe can't tell you exactly where an electron will appear because it hasn't finished computing that answer yet. It's still deciding, or perhaps the randomness points to something external. If the universe is a calculation being performed by some larger system, some higher dimensional computer or mathematical structure, then quantum uncertainty might be the place where that external reality shows through. The random fluctuations might be inputs from outside, perturbations from a realm beyond our space and time, hints that our reality is embedded in something greater. We don't know, and that uncertainty itself is revealing. For 3 centuries, physics promised us that mathematics could describe everything, that the universe was a solvable problem, that given enough time, enough data, enough computational power, we could predict any outcome, answer any question. But quantum mechanics says no. There are questions the universe itself hasn't answered. There are outcomes that aren't determined until the moment they occur. There are properties that don't exist independently of measurement. The closer we look at reality, the more it seems to blur. The sharp edges of classical physics dissolve into probability clouds. The deterministic machinery reveals itself as something stranger, more fluid, more fundamentally uncertain. Does this mean the universe isn't mathematical after all? That our elegant equations are just approximations, useful fictions we tell ourselves while the real universe operates according to principles we can't express in numbers? Or does it mean we're discovering a deeper mathematics, a mathematics of possibility and superposition and entanglement? A mathematics where certainty itself is the exception, not the rule? Perhaps the quantum world is showing us that mathematics isn't just about calculation. It's about structure, pattern, relationship. And those can exist even in the presence of uncertainty, even in the presence of what we call randomness. The wave function, after all, is perfectly mathematical. It's what happens when the wave collapses that defies prediction. But the collapse itself follows rules. The probabilities are precise. The patterns are exact. So maybe the universe is calculating. Maybe it's running an endless computation, working out the consequences of its own laws moment by moment. And maybe what we call quantum randomness is simply the edge of that calculation, the boundary where determined past meets undetermined future. Or maybe we're still missing something fundamental, some deeper principle that would make sense of it all, some larger framework that would show us how randomness and mathematics fit together, how observation and reality connect, how the quantum and the classical emerge from a single unified picture. We're still looking, still measuring, still calculating, still trying to read the mind of the universe and the behavior of its smallest parts. But the quantum realm guards its secrets jealously, and as we peer deeper into the mathematical structure of reality, we begin to wonder if the equations themselves might be pointing beyond themselves, toward a question even more fundamental than the ones we've been asking. If the universe is mathematical, and if its mathematics includes genuine uncertainty, genuine randomness, genuine choice at the quantum level, then perhaps the real question isn't who is doing the calculating. Perhaps the question is whether the calculation can calculate itself into existence. What is the universe made of? For most of human history, the answer seemed obvious: matter, substance, stuff you can touch, see, hold in your hand. Atoms, molecules, the solid architecture of reality. Then we discovered energy, learned that matter and energy are interchangeable, two forms of the same underlying thing. Einstein's famous equation, energy equals mass times the speed of light squared, united them into a single framework. But in recent decades, a more radical possibility has emerged. What if matter and energy are themselves secondary? What if the deepest layer of reality isn't substance at all, but something more abstract, more fundamental? What if everything is information? The physicist John Wheeler spent his final years contemplating this question. He coined a phrase to capture it, 3 words that sound like a riddle. It from bit. Every it, every particle, every field of force, every aspect of the physical world derives its very existence from binary choices, from yes or no questions, from bits of information. Reality, Wheeler suggested, emerges from answers to questions. The universe is not made of matter that processes information. The universe is information that manifests as matter. It's a profound inversion of everything we thought we knew. Think about what information is. It's not a thing, it's a difference, a distinction, a pattern. When you flip a coin and it comes up heads, information has been created, not because anything material has been added to the universe, but because a question has been answered. A binary choice has been made. One bit of information now exists where before there was only uncertainty, and that bit is real. It has consequences. It can be transmitted, stored, processed. It can cause things to happen. In fact, information is the only thing that can't be destroyed. This realization came from one of the strangest places in physics: black holes. When a star collapses under its own gravity, crushing matter to infinite density, it creates a region of space-time so warped that nothing can escape, not even light. We call it a black hole. And for decades, physicists believed that black holes were the ultimate destroyers. Whatever fell in was gone forever, erased from the universe. But then Stephen Hawking discovered something strange. Black holes aren't perfectly black. They emit radiation, slowly evaporating over incomprehensible spans of time. And this raised a terrifying question. What happens to the information that fell in? If a book falls into a black hole, and the black hole eventually evaporates into random thermal radiation, has the information in that book been destroyed? Has the specific arrangement of letters, the precise sequence of words, simply ceased to exist? According to the laws of quantum mechanics, that's impossible. Information is conserved. It can be scrambled, encrypted, hidden, but never truly destroyed. It's as fundamental a law as the conservation of energy. This paradox consumed physicists for decades, the black hole information paradox. And its resolution pointed towards something extraordinary. The information isn't destroyed, it's encoded on the surface. Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder or hidden information. And remarkably, this entropy is proportional not to the volume of the black hole, but to the area of its surface. The event horizon, the boundary beyond which nothing can escape. It's as if everything that falls into a black hole is somehow written on its surface, encoded in the quantum structure of the horizon itself. This led to one of the most startling ideas in modern physics, the holographic principle. Imagine a hologram, a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. The holographic principle suggests that our entire universe might work the same way, that all the information describing everything within a volume of space might be encoded on the surface that bounds that volume. Reality, in this view, is like a holographic projection. We experience a three-dimensional world, but the fundamental information defining that world exists on a two-dimensional boundary. It sounds like science fiction, but the mathematics works, and it suggests something profound about the nature of reality. If the universe can be fully described by information on a boundary, then space itself might be emergent, not fundamental, but derived. A convenient way of organizing information, like the folders on a computer desktop. The folders feel real, feel like they exist independently, but they're just a visualization of underlying data. Perhaps space-time is the same, a user interface for information. And if information is primary, if it's the true substrate of reality, then we need to ask, what is information doing? How does it behave? What are its laws? Information can be measured. Claude Shannon, the father of information theory, showed us how. 1 bit is the answer to a yes or no question. 8 bits make a byte. 1,000 bytes make a kilobyte. The numbers scale up from there, quantifying exactly how much information any system contains. Information can be transmitted. It flows from place to place, moving through space at speeds limited by the speed of light. When you speak, information travels from your brain through sound waves to someone else's ear. When you read this, information is flowing from these words into your mind. Information can be processed. It can be transformed according to rules, combined, separated, copied, compared. Computers process information trillions of times per second, following algorithms, executing programs, and information can be stored, encoded in atoms and magnetic fields, in the spin of electrons, in the quantum states of particles. Every system that has distinct possible states can store information. Now ask yourself, what if that's all the universe is doing? What if the cosmos is a vast information processing system? What if every particle interaction, every quantum measurement, every collapse of a wave function is a computational step? What if the laws of physics are algorithms and reality is the output? It's not as wild as it sounds. We already know that physical processes can compute. Your brain computes, your smartphone computes. Even simple systems, like patterns of ripples on water, perform computations, solving equations through their physical evolution. And the universe is certainly processing information. Every moment, countless interactions occur. Particles collide, fields fluctuate, wave functions collapse. Each event transforms the information state of the system. Each moment is, in a sense, an update. The physicist Seth Lloyd has calculated how much computation the universe has performed since the Big Bang. The answer depends on how you define a computational operation, but by one reasonable measure, it's approximately 10 to the power of 120 operations. A 1 followed by 120 zeros. That's how many times the universe has updated itself. How many elementary computational steps have occurred across all of space and time? The universe, in this view, is running a program, not metaphorically, literally. The laws of physics are the code. The quantum fields are the variables. And reality is what the program outputs moment by moment across 13.8 billion years of runtime. But if the universe is a computation, we need to ask, what kind of computation? Is it deterministic, following a fixed algorithm from initial conditions to inevitable conclusion? Or does it incorporate randomness, using quantum indeterminacy as a random number generator? Is it solving a problem? Optimizing something? searching for something? Or is it simply evolving, computing its own future for no purpose other than to exist? Some physicists have gone further. They've suggested that the universe isn't just performing a computation, it is a computation. That matter and energy in space-time are all emergent properties of an underlying computational process. That if you could somehow peer beneath the surface of reality, you wouldn't find particles or fields or even information in the abstract sense. You'd find processing, calculation, operations being executed according to rules. The physicist John Archibald Wheeler, who gave us it from bit, also gave us another phrase, the participatory universe. He believed that observation, measurement, the act of extracting information from a system isn't separate from reality. It is reality. The universe is a self-excited circuit, a feedback loop where information creates matter, matter encodes information, and observation brings both into being. We're not outside observers looking in. We're part of the computational process. Our observations are computational operations. Our measurements are updates to the universal information state. Consciousness itself might be a pattern of information processing. Your thoughts, your memories, your sense of self all emerge from the flow and transformation of information in your brain. And your brain is made of atoms, which are patterns of quantum information, which means you are, in a very real sense, information that has organized itself to process information, the universe computing itself, and in doing so, creating subsystems that compute, creating us. It's dizzying to think about, but it also explains something that's always been mysterious, why mathematics works so well at describing reality. If the universe is fundamentally computational, if it's information being processed according to rules, then of course mathematics describes it perfectly, because mathematics is the language of rules, of structure, of logical operations. Mathematics is computation in its purest form. The universe isn't described by mathematics. The universe is mathematics, running itself, updating itself, calculating its own existence instant by instant. But this raises the question we've been circling around since the beginning. If the universe is a computation, who or what is running it? Is it self-executing, a bootstrap process that somehow initiated itself? Or does it require something external, some computational substrate on which the program runs? And if there is something external, some larger system executing the computation we call reality, what does that make us? Information is strange. It exists at the boundary between the physical and the abstract. It's real enough to be conserved, to have consequences, to shape the evolution of the cosmos. But it's not substantial. You can't hold it. You can't point to it and say, there, that's information. Information only exists in relation, in patterns, in differences that make a difference. And that means information blurs the line between what's real and what's represented, between the thing itself and the description of the thing, between reality and something that merely encodes reality. A hologram looks three-dimensional, but it's actually flat. The depth is an illusion, a trick of light and interference patterns, yet the information describing that depth is real, is genuinely there, encoded on the surface. So, which is more real, the three-dimensional image you perceive, or the two-dimensional surface that contains its information? The question stops being simple when you realize we might be asking it about ourselves. If we are patterns of information, if our thoughts and experiences are computational processes, if the very matter we're made of is emergent from underlying information and states, then what's the difference between existing and being simulated? What's the difference between a universe that computes itself into existence and a universe that's being computed by something else? What if our reality, with all its matter and energy and space-time, is information being processed on a substrate we can't perceive, in a space we can't access, according to rules that govern something larger than our cosmos? What if the universe isn't just mathematical? What if it's virtual? There's a thought experiment that haunts modern physics. Imagine a civilization far more advanced than ours, perhaps 1,000,000 years ahead, perhaps 1 billion. They've mastered physics, conquered entropy, harnessed energies we can barely imagine. And with that power, they decide to create something extraordinary, a simulated universe, not a crude video game or virtual reality environment, but a complete cosmos, with its own space, its own time, its own laws of physics. They write the code, set the initial conditions, and let it run. Stars form, galaxies spiral, planets coalesce. And on at least one of those planets, life emerges. Eventually, consciousness. Eventually, beings like us, looking up at their sky, asking questions about the nature of their reality, never suspecting that everything they see, everything they are, is information running on someone else's computer. The question that follows is simple and terrifying. How do we know we're not in that simulation right now? This is the simulation hypothesis. And contrary to what you might think, it's not a fringe idea dismissed by serious scientists. It's been debated by physicists, philosophers, and technologists at the highest levels. Because once you accept that the universe is fundamentally computational, that reality is information being processed according to rules, the line between a self-executing cosmos and a programmed one becomes impossibly thin, perhaps invisible. The philosopher Nick Bostrom formalized this into an argument that's difficult to dismiss. He suggested that at least one of three propositions must be true. First, civilizations like ours almost never reach the technological capability to create realistic simulations of universes with conscious beings. Second, civilizations that reach that capability almost never choose to create such simulations. Or third, we are almost certainly living in a simulation right now. The logic is elegant and disturbing. If advanced civilizations can create realistic simulations, and if they choose to create them, then simulated universes would vastly outnumber real ones. For every original universe, there could be thousands or millions or billions of simulated ones, which means, statistically, you're far more likely to exist in a simulation than in base reality, unless something prevents it, unless the technology is impossible, or the ethics insurmountable, or the computational resources too expensive even for godlike civilizations. But if none of those barriers hold, then probability suggests we're living in rendered reality, in code. It sounds absurd, but then you remember that we're already creating simulations. Crude ones, yes, with blocky graphics and simple physics. But our games and virtual worlds grow more sophisticated every year. We're learning to model reality computationally, to create spaces that feel increasingly real to those who inhabit them. And we're nowhere near the limits of what's possible. Now imagine what a civilization could do with computers billions of times more powerful, with quantum processors that harness the full computational power of quantum mechanics. With computational substrates we haven't even imagined yet. Could they simulate a universe so detailed, so complete, that a simulated beings inside would be genuinely conscious, would feel, think, wonder, suffer, and love? The uncomfortable answer is, we don't know why not. And if they could, wouldn't we? Wouldn't we create ancestor simulations, running histories forward from different initial conditions to see what emerges? Wouldn't we create entire universes just to explore the space of possibilities, to watch evolution unfold, to understand our own origins? Wouldn't we want to meet God by becoming one? But if our universe is a simulation, there should be evidence. Glitches in the matrix, computational limits, places where the program shows through. And strangely, there are candidates. The speed of light, for instance. Nothing can travel faster. It's not just a speed limit for matter. It's a speed limit for information, for causality itself. Why should such a limit exist? In base reality, perhaps it shouldn't. But in a simulation, bandwidth matters. Processing power is finite. If information could propagate instantaneously, the entire simulation would need to be updated simultaneously. But with a maximum speed for information transfer, you can update the simulation locally, dealing only with regions that are causally connected. The speed of light might be a frame rate. Then there's quantum mechanics itself. the way particles exist in superposition until observed, collapsing into definite states only when measured. It's deeply strange from a realist perspective, but from a computational one, it makes perfect sense. Why render details that no one is observing? Why calculate the exact position of every particle when you can store them as probability distributions instead, only computing specific values when something in the simulation needs to know? It's like a video game that only renders what the player can see. Look away, and the computational detail drops. Turn back, and it fills in seamlessly. The universe does something similar. It maintains quantum uncertainty until observation forces a measurement, until the simulation needs to return a specific value. And then there's the Planck scale, a fundamental limit to how small distances can be, how brief time intervals can be. Below the Planck length, about 10 to the negative 35 meters, our physics breaks down. Below the Planck time, about 10 to the negative 44 seconds, space-time itself becomes uncertain. These might be the pixel size, the minimum resolution of the simulation, the point where you can't zoom in any further because there's nothing smaller to render. Of course, these could all be features of base reality too. Natural limits imposed by the fundamental structure of the cosmos. There's no way to prove their computational constraints rather than physical ones. But the fact that they exist at all, the fact that reality seems to have built-in limits that would be necessary for a simulation, is at least intriguing. Some physicists have proposed experiments, ways to test if we're in a simulation. Look for anomalies in the cosmic microwave background, the afterglow of the Big Bang. Search for patterns that might indicate we're at the edge of a rendered region. Check if physical constants actually vary slightly, as they might if the simulation is running on finite precision arithmetic. So far, we've found nothing conclusive, but we're only beginning to look. And even if we found evidence, what would it mean? If our reality is a simulation, who or what created it? The immediate answer might be a more advanced civilization, post-humans, aliens, some form of intelligence that evolved in a universe more real than ours and chose to create new ones. But that just pushes the question back. Where did they come from? Is their universe real, or is it also a simulation? And if it's also a simulation, who simulated them? You could have simulations within simulations within simulations. Layers of reality, each one created by the layer above. Turtles all the way up. At some point, presumably, there's a base reality, a first mover, an original unsimulated universe where conscious beings first emerged and gained the power to create new worlds. But what if there isn't? What if the chain is circular? What if our simulation eventually develops the technology to create simulations of its own, and somewhere down that line, one of those simulations creates the universe that originally created us? It sounds impossible, but causality might work differently at the level of simulations. Time might not flow in a single direction across all levels. The creator might exist in the future of their creation. Or perhaps the creator isn't a civilization at all. Perhaps it's something we've been circling around this entire time, something older than the concept of simulation, dressed now in the language of computers and code, a deity. The simulation hypothesis, stripped of its technological aesthetics, is structurally identical to certain theological ideas. An intelligent creator who brings a universe into existence, who defines its laws and sustains its operation, who exists outside of space and time, observing everything, aware of everything. God as programmer, creation as computation. It's an uncomfortable convergence, science fiction meeting scripture, the divine rendered in the language of information theory. But perhaps that's not surprising. Humans have always imagined creation in terms they understand. Ancient cultures saw gods as craftsmen, sculpting reality from clay or chaos. The Enlightenment saw God as a watchmaker, at winding up a mechanical universe. Now, in the age of information, we imagine creation as code. The metaphors change. The question remains. If something outside our reality created it, set it running, defined its rules, what does that make us? Thoughts in a cosmic mind? characters in an elaborate story, experiments in a vast laboratory, or something the creator never intended, emergent complexity that surprised even them? And what does the creator want? Are we being observed, judged, guided, or did they simply start the simulation and walk away, letting it run to completion without intervention? Maybe there are clues in the code itself. Maybe the laws of physics, the constants that define our universe, encode a message, a signature from the programmer, a way to signal to any conscious beings that emerge, yes, you were created. Yes, there is something beyond. Or maybe not. Maybe the simulation is entirely self-contained. Maybe the creator, if there is one, has no way to communicate with us. Maybe we're sealed inside our computational bubble, unable to access anything beyond the information we're made of. The simulation hypothesis forces us to confront something unsettling, the limits of empirical investigation. If our universe is a simulation, and if the simulation is sufficiently complete, there might be no way to detect it from the inside. No experiment we could perform, no observation we could make that would reveal the truth. We might be forever trapped in epistemic uncertainty, able to wonder but never to know. And yet, we continue to look, continue to question, continue to probe the boundaries of reality, searching for seams, for glitches, for any hint that there's something beyond. Because that's what consciousness does. It asks, it seeks, it refuses to accept the given without interrogation. Perhaps that's what we're for. Perhaps consciousness is the universe looking at itself, or the simulation examining its own code, information that has organized itself to the point where it can reflect on its own existence. We are the cosmos becoming aware, the calculation that has learned to question who's calculating. And maybe that's the point. Maybe the reason for all of this, for the mathematics, for the information, for the vast computational machinery of existence, is simply to create beings capable of asking these questions. Beings capable of looking back at their creator and saying, "We see you, we know we're made, and we want to understand why." If the universe is programmed, perhaps consciousness itself is the program's way of looking back at its maker. There is one phenomenon we haven't fully accounted for, one variable that appears nowhere in our equations, yet without which the equations themselves would have no meaning. Consciousness. The fact that you are here, now, experiencing these words, not just processing them mechanically like a computer might, but understanding them, feeling their weight, wondering about their implications, the subjective inner experience of being someone, of having a perspective, of existing from the inside. We've traced mathematics through the cosmos, found it in the spiral of galaxies, the decay of particles, the information encoded in black holes. We've considered whether the universe is a calculation, whether reality might be simulated, whether everything reduces to information being processed according to rules. But who is it that notices? Who reads the output of the cosmic computation and finds it beautiful? Who looks at the equations and wonders what they mean? Who asks the question we've been circling since the beginning? If the universe is mathematical, who is doing the calculating? The answer might be staring back at us from the mirror. Consciousness is the deepest mystery we face. Not because it's complex, though it certainly is, but because it's the one thing we know with absolute certainty exists, yet can't explain within our current framework of physics. You can doubt whether the external world is real. You can question whether other people are truly conscious or merely sophisticated automatons. You can even doubt whether you existed a moment ago, whether your memories are real or implanted, but you cannot doubt that you are experiencing something right now, that there is something it is like to be you in this moment. That awareness, that inner light of subjective experience is the most undeniable fact in the universe, and yet we have no idea what it is. Science can map the brain, can trace neural pathways, measure electrical signals, watch regions activate and quiet in perfect correlation with thoughts and feelings. We can explain how information flows through neural networks, how memories are encoded in synaptic connections, how decisions emerge from distributed processing across billions of neurons. But nowhere in that description does consciousness appear. Nowhere do we find the experience itself, the feeling of what it's like. We describe the mechanism, but the phenomenon remains untouched. The philosopher David Chalmers called this the hard problem of consciousness. The easy problems are things like explaining how we discriminate stimuli, integrate information, report mental states. These are just matters of finding the right mechanisms, tracing the right neural pathways. The hard problem is explaining why any of this feels like something, why there's an inner experience at all. Why isn't the universe just information processing in the dark? Why is there light? Some scientists believe consciousness is simply what complex information processing feels like from the inside. That when a system reaches a certain threshold of integration, of self-reference, of recursive modeling, awareness emerges as a natural property. Consciousness in this view is what it's like to be a sufficiently complex computation. But that doesn't explain why there should be anything it's like at all. Why would electrons flowing through circuits produce an inner experience? What is it about certain physical configurations that switches on the light of awareness? Others suggest consciousness is more fundamental, that it's a basic feature of reality, like mass or charge, that even elementary particles have some primitive form of experience, and complex consciousness is what you get when trillions of these micro-experiences combine and integrate. Panpsychism, the idea that mind is everywhere, woven into the fabric of existence, that the universe is not just mathematical, not just computational, but experiential all the way down. It sounds mystical, but it solves a problem. If consciousness is fundamental, you don't have to explain how it emerges from unconscious matter. It was always there, waiting to organize itself into more complex forms. And it would mean we've been asking the wrong question. We've been asking how the universe calculates. But perhaps the universe isn't calculating at all. Perhaps it's experiencing. Think about what happens in quantum mechanics. The wave function describes all possible states of a system, existing in superposition until an observation occurs. Then the wave collapses. The many possibilities become one actuality. The Copenhagen interpretation, remember, placed observation at the center of this process. Not mechanical measurement, but conscious observation. The universe, in this view, exists in quantum limbo until a conscious being looks at it. Most physicists now reject this idea. They argue that any interaction, any measurement, even by an unconscious device, collapses the wave function. Consciousness isn't necessary. But what if they're wrong? What if consciousness isn't an accidental byproduct of complex matter, but an essential ingredient in the functioning of the universe? What if observation by a conscious being truly is different from mechanical interaction? John Wheeler proposed a participatory universe. He argued that consciousness isn't separate from physical reality, but woven into it, that the universe is a self-exciting circuit, where the present creates the past through observation. Quantum measurements made now reach backward through time, selecting which history actually occurred. It's a strange idea. But quantum mechanics already tells us that particles can be entangled across space, influencing each other instantly regardless of distance. Why couldn't events be entangled across time, with future observations affecting past states? In this view, we're not passive observers of a pre-existing universe. We're active participants. Our consciousness doesn't just witness reality, it helps create it. Every measurement, every observation, every moment of awareness is a choice point, where possibilities collapse into actuality. We are the universe deciding what it will have been. But this raises a question even more profound. If consciousness participates in creating reality, where does consciousness come from? The materialist answer is from the brain. Consciousness is produced by neural activity, an emergent property of biological computation. We're complex information processors, and consciousness is what that processing feels like from the inside. But if consciousness helps determine physical reality through the observer effect, then consciousness can't just be a product of physical processes. That would be circular. How can the brain produce consciousness if consciousness is necessary to collapse quantum states into the definite physical configurations that make brains possible? Unless consciousness is both effect and cause, product and producer. A strange loop, in the words of Douglas Hofstadter, where consciousness arises from the material world, even as it participates in creating that world through observation. The calculator calculating itself into existence. Or perhaps we've been thinking about this wrong from the beginning. Perhaps the question isn't whether consciousness arises from matter or matter arises from consciousness. Perhaps they're two aspects of the same underlying reality, like information. Information is neither purely physical nor purely abstract. It exists at the boundary in the relationship between different states, in patterns of differences. Consciousness might be similar, not matter, not spirit, but something that emerges when information becomes self-referential, when a system becomes complex enough to model itself. You are a pattern of information that has learned to recognize itself as a pattern. Your consciousness is the universe folding back on itself, creating a knot of self-awareness in the fabric of existence. And if consciousness is information aware of itself, then every time you think, every time you experience anything at all, you're participating in the cosmic calculation. You're not separate from the mathematical structure of reality. You are part of it, an active term in the equation, the universe computing itself, and in doing so, becoming aware. This would explain something that has always been puzzling. Why does consciousness feel so different from everything else? Why does subjective experience seem to occupy a different category than objective physical processes? Because it does. Consciousness is the view from inside the computation. It's what information processing feels like when you are the information being processed. It's the difference between describing a calculation from outside and being the calculation. We've spent this entire journey looking outward, examining the mathematics of stars and atoms and quantum fields, tracing information through black holes and simulations. But perhaps the most important mathematics has been here all along, inside, in the very fact that we can look and trace and wonder. The equations led us outward, across cosmic distances, down into quantum foam, through layers of abstraction and information and code. We searched everywhere for the calculator, for the source of the mathematical structure we see everywhere we look. But maybe we've been searching in the wrong direction. Maybe the calculator isn't outside the universe looking in. Maybe it's inside, distributed across billions of nodes of awareness, each one a local instance of the cosmos becoming conscious of itself. Maybe every time a child looks up at the stars and asks why. Every time a scientist traces an equation to its logical conclusion. Every time anyone anywhere becomes aware of the deep mathematical structure underlying reality. That's the universe calculating itself. That's consciousness performing its function in the cosmic algorithm. We are not separate from the question. We are the question asking itself. And maybe that's what consciousness is for. Maybe it's not an accident of evolution, not an incidental byproduct of brains complex enough to navigate hostile environments. Maybe it's the point, the purpose, the reason the mathematical universe bothered to instantiate itself in matter and energy and time, so it could know itself, so the calculation could become aware of the calculator, so the question could finally turn inward and discover that the answer was never out there at all. The equations led us outward to galaxies and quarks, to the very edge of space and time, but the final variable may reside within.